Welcome back, everyone. In this video, I'll begin going over the lecture for the integration by substitution section. Right. Now, to start, really what integration by substitution is, it's going to be the first integration technique. And it's the first one and the only one for a while because there are a lot of applications of integrals that only really require substitution method. There are a lot of other methods which you can see in the future, but substitution method is by far the most important method. And with a lot of our applications going forward, you actually need to be able to use substitution method no matter what you're dealing with because of the application. Right. So this example here, I just wanted to talk about why new integration techniques are needed in general. And it basically boils down to the fact that if you don't have one of those integral formulas, so look down here, we have the integral of sine cubed of x times cosine of x dx. You don't have a formula to tell you what is the integral or what is the antiderivative of this. And at this point, that's all we have. If we can't make this into something that we have a formula for, then we're kind of stuck. And the thing about this one is there's no way you're going to work around it. You have to use a new method. And the method for this one, which I'll talk about again, is going to be integration by substitution. Now, there are a bunch of different methods. So as you learn about more and more methods, you might look at this one and realize that it can be covered in a different way as well, which is fine. Right. And really, I want to go ahead and just talk about, specifically the substitution method now. How to really approach it is the main point. All right, so I want to go ahead and talk through this example, and then after I talk through this example and the build-up, I'll actually work it out for you. So in order to understand the idea of the substitution method, we'll look back to this example above. And what the substitution method is, it's similar to the chain rule for derivatives. So the substitution method is similar to the chain rule for derivatives. And you'll pretty much see it as we work through a problem. But the idea is if you are multiplying a function by something that can look like the derivative of the inside. So we know the chain rule, when you do the chain rule and you do the derivative of something requiring the chain rule, you always multiply by the derivative of the inside thing. Well, if you have something that looks set up like this, so this is sine cubed of x and we're multiplying by cosine of x, what's going to happen here is if we can see that we have some sort of inside, its derivative is over here, then it's a good indication you should use the substitution method. Okay. Now, to get more specific about this problem, when we're talking about doing an antiderivative, we're talking about this being the derivative of something and we want to find the original function. So relating it back to this, what we're really saying is we have f prime of x equals sine cubed of x times cosine of x. And I just want to talk about what I see here and why I would know I need to use the substitution method. Well, I notice that we are multiplying the sine cubed of x part by cosine of x. And the inside of sine cubed of x is just sine of x. Now, we don't often write the powers of trig in another way, but sine cubed of x, we know is the same as sine of x all cubed. And so really the inside function is sine of x. Well, luckily for us, and it's going to have to be set up this way to do this problem anyway, but lucky for us, the thing we're multiplying by over here, cosine of x, is the derivative of sine of x. So the derivative of the inside, the derivative of sine of x is cosine of x. And that's exactly what we have over here. And that's what's going to indicate to me I need to use the substitution method, is because if I look at this thing, I have some sort of inside. The inside of it is sine of x. The derivative is cosine of x, and I'm multiplying by that. Right. Now I'm going to leave this in view and just sort of go through the process, and we can read along together here of what you do with the substitution method. What you do is you identify the inside. So these are really going to be the steps for the substitution method. And you set u or a different letter, but it's commonly u. You set it equal to the inside function. So for our problem here, what I identified was that the u should be sine of x. So I say u equals sine of x. Well, one thing that's definitely extra compared to doing the chain rule is because we're working backwards, yet we actually have to compute the derivative of u as well. Specifically, we have to do the differential. So next we compute the differential. And it's been a long time since we did it, but remember the differential is just the derivative of the function. So it's f prime of x and then times dx. Remember, we kind of reorganized the equation du over dx, but probably before we used dy over dx equals f prime of x, and we multiplied each side by dx to get this. So I don't want to actually write this because when you compute a differential, you're really computing this thing. But when we say f prime of x, what we're talking about is f of x being what we set equal to u. Okay, so since f of x is equal to u, f prime of x equals cosine of x. And that means du, if we plug that in, equals cosine of x dx. Okay. And I'll just write this in green to match what we set in u. So du equals cosine of x dx. All right, once you have your u and your du identified, you can do a couple things. One thing is if you have a perfectly matched thing, so you can notice here that we have cosine of x dx is what du is. So this whole thing is going to be du. But what always works is if you solve for dx here. This is an extra step in this problem, but as we do other ones, it might be helpful to realize you can do this. If you solve for dx by dividing by cosine of x here, what we have is we have dx equals du over cosine of x. Now, a lot of books and a lot of places might not tell you to do this or describe this step because they want you to realize that it's right here. Well, what if you have a 2? What if you have a 1/2? What if you have something else? The easiest thing to do is mess that up. If I have a 2 here, what do? Is du going to have a 2 on it, or is it going to have a 1/2? If I have a 1/2 here, same idea. Well, if you do this, then you don't have to really worry about it. Right, but once you do these two things, you figure out what u is, compute the differential, and then solve for dx. What you want to do is plug in for u and dx. Now, what we say here when we say plug in for u and dx is we only want u and du inside. We no longer want to see x inside our integral after we do substitution. So what I'm going to do is I'm going to start with just write down the integral we have at the beginning. We have sine cubed of x times cosine of x dx. And then we identified what u should be. U should be sine of x, so this is u cubed. And then because I am doing this extra step, but I'll show you that it all works out, I can't plug in all at once for cosine of x dx. I mean, I can because I have the equation here, but like I described before, you might have something extra here and it's really easy to mess up the canceling part. So what I do is I leave the cosine of x here. So cosine of x is not related to u. And then in place of dx, I go ahead and plug in my formula, which is du over cosine of x. And as long as you do everything correctly, the correct substitution, everything with x should go away, and cosine of x perfectly cancels out, and we integrate now a much simpler formula. What are we integrating? We're integrating u cubed du. Well, this is just about as easy as an integral gets because this is just the power rule. So now we can integrate this. So just because we're using a different letter from the beginning doesn't mean we can't do it. The important thing is that you have a u cubed and you have a du. If you had u cubed but with dx, you can't do it. It doesn't make any sense. You have to make sure you plug in both parts. All right, so when we integrate this, we do the power rule. We add 1 to the power, divide by the new power, and then because it's an indefinite interval, we add our constant. Well, the last thing you want to do here after you integrate is you don't want u in your final answer because you started with the x's, you want x's in your final answer. So you need to plug back in what u is. But luckily for us, u is just sine of x. So when we plug that in, we get sine of x to the 4th over 4 plus c. And there's nothing wrong with this answer. You can leave it exactly like this. If you prefer to pretty it up, you can bring the 1/4 in front, and you can bring the power on the sine to its normal spot. So you can write a sine to the 4th of x plus c. But either one of these is perfectly fine. And that's how we do the substitution method. As you practice the substitution method, you'll get a lot better at recognizing that you have to do it at the beginning. But pretty much the point here at this point is that if you don't have a rule for integrating, so we don't have a rule for integrating multiplications, which means we can't look at each part. We have to look at this all at once. We definitely don't have a rule for how to integrate sine cubed of x. We do have a rule for integrating just cosine of x or just sine of x, but not some combination of like this. What you have to do is think about the substitution method. Often this is called u sub or u substitution because the common letter to substitute with is u, but you can use any letter at all. And a big thing is that if your problem starts with u's, which can happen, you can't use u over again because it's already used. So I can use any letter here as long as it's not x to substitute with. Right. Now, one thing you might want to do, especially with integration, is you can check your answer by doing the derivative and seeing does it match. So this is a completely optional thing. But if we want to check our answer, what we do is we take our answer here and we do the derivative of it. So d over dx of 1 over 4 times sine to the 4th of x plus c. Well, we've done plenty of derivatives, so we know the 1/4 will stick there. The derivative of a number is just 0. Remember, c is just a number, whatever it is. When we do the derivative of sine to the 4th of x, we get 4 times sine cubed of x because we subtract 1 from the power. And then the derivative of the inside is sine of x. The derivative of sine is cosine of x. And if you look at this, the 4's cancel, and we get exactly sine cubed of x times cosine of x, which was exactly the inside. It is matching, and that means we are good to go. Okay. Now, you don't have to check your work, but it is nice, and it's always good to work on your derivatives, practice them, because it is a part of these problems. Whenever you compute du, you're always going to be doing a derivative. All right, so with that, let's go ahead and start working on the problems. And of course, in this section, everything's probably going to be based around using the substitution method, but you want to make sure you recognize why you're using it, what you're using. One of the easiest examples, in my opinion, is that when you have a natural log, you don't have a formula for the natural log antiderivative. There is one, but we don't have it yet because it takes a different, completely new technique that we don't know yet. So this is kind of a big hint at this point, but it's pretty much always going to be true if you need to do the antiderivative or integral with ln of x. U equals ln of x almost always will work. Now, it does have to be set up in a particular way to work, but it's got to be set up so that it does work, because there are tons of functions that actually you cannot integrate, and we talked about that in a previous section. All right, so with that one, I want to go ahead and do exactly what I said. This is the natural log of x all to the 5th power over x dx. Well, we definitely don't have a formula for that, but because I don't have a formula for the natural log at all, let's go ahead and just make u equals to the natural log of x. But a good indication of anything is that if you have a power, almost always when you do substitution method, the thing that's inside the power is going to be your u. We just got to hope that when we do the du part, it works out well for us. All right, so we choose u equals the natural log of x. Now we do the differential du. The derivative of the natural log of x is just 1 over x. And then the differential part says multiply this by dx. And at this point, it's up to you again. You can directly substitute because we actually have a 1 over x dx perfectly in here. This is like a 1 over x. Or you can do what I did last time. And it is just one extra step. So in my opinion, it's worth it to solve for dx. Once again, it's not necessary, but I think it's just worth it. So when we do that, we get x times du, because we can multiply x on each side. Get that to cancel. We get x times du equals dx, and that's what we're going to plug in. So everywhere we see the natural log of x, we're going to put u. Everywhere we see dx, which should only be one place because you can never have more than one dx in an integral, we want to put x times du. So that was the third step. We figure out what u should be, compute du, solve for dx, and then plug it in. So let's go ahead and we integrate. I'll go ahead and just rewrite our problem here. So we have the natural log of x all to the fifth over x dx. Well, what we have here on the top now is u to the fifth because the natural log of x is u over x. I mean, we didn't really try to plug in anything for x here. Our hope is that it just goes away. Well, dx is x times du. And luckily for us, the x's all perfectly go away. That goes away with that one. So we have just u to the fifth du. And now you can finish this up. Add 1 to the power, so we get u to the sixth over 6 plus c. And then the last step here, not to forget, we started with x's, we want to end with x's. Go ahead and plug in what u is. U is the natural log of x. We get the natural log of x to the 6th power over 6 plus c. And that's it. Right. So I'll stop here, but in the next video, we'll practice a lot more because this one had a pretty big hint at the beginning. We pretty much have to use the natural log of x, but you can kind of see why. Is that the derivative of the natural log is 1 over x. So this x is really taking care of that 1 over x part for us because it's in the bottom. You know, one thing you might ask yourself is, what if this was x squared or any other power of x? That's a fair question, and this problem becomes very hard, if not impossible to do. So keep in mind, you're not going to be asked to do a problem that it's not going to work out. The main goal of this section is that you can start to see and learn what is u, what should you make u, and that's really the main point. And just to really drive the point home of why you really need everything to work out, I went ahead and just typed in Wolfram alpha. If you integrate this, but with x squared on the bottom, what do you get? Well, you get this really, really, really long answer. It looks nothing like ours. So right there, it should tell you this is going to be really, really hard to do. But it also says something weird. It says, assuming a complex valued logarithm. Now, you've probably seen complex numbers, but not involving logarithms. And those are very complicated, and we don't really deal with complex numbers when we're in calculus, at least the beginning of calculus. So that you can be assured that this is not something we can figure out by hand, at least in a realistic fashion. All right, so just keep that in mind. Everything will work out perfectly. You just really need to figure out what you should be. And with that said, I'll see you in the next video.